as I was mentioning, test 3 was that we did on Monday. I've only received a few of them in so far. I've got those graded and I'm waiting for some more to come in. As soon as I get those in, I will get them graded and back to you as fast as I can. Test 3 typically is a little bit lower scores than the other because this is really the first completely new material for most of you. And the processes take a while to get used to. So, and it's kind of a long test, I admit that. So we make sure that once I get those back to you, you still do corrections. And then those corrections, you get up to half your points back. And we'll see once all the other tests come in. A lot of times I offer an alternative retake on this. And what that is just an alternative version of the test that I let you take home and work on and bring that in. And what I do is I'll do two things. For the corrections, you still get back half your points. If you do the retake, again, you get to take that home and work on it, have a couple days to do it. Then I will average that in with your score as well. So it is possible to get back up to 3/4 of your points on this test as we do that. But I'm going to hold off on offering that alternative retake until I have everybody's in and scored and graded. And then I'll just probably post that in Blackboard for you. So now as we're doing Unit 4, which we're starting today, Unit 4 is on graphing. And there's going to be a couple of different types of graphing. We're going to talk about algebraic graphing, which is really the heart of the class. We're going to probably spend 4 or 5 hours on that, maybe even a little bit more. And then we'll talk about data graphing, which really only takes about a class to get through. I may have to look into Unit 5 a little bit and talk about organizing data a little bit to talk about those data graphs, but they're pretty simple. That's mostly stuff you've seen before. And then there's a little bit in there on relationships between variables. And that's actually a very powerful, that variable relationships is a very powerful tool as you move forward. My background is engineering, and that the variable relationships variation really is the concept involved. Is one of the more powerful tools as you go back and go forward to try to apply math, just because of the variety of things that can be applied in. Okay, so let's take a look at the beginnings of our new material. Like I said, we'll talk more about test 3 once I have all of them and I have them graded. So what we're looking at today is we're looking at displaying relationships really between numbers. And we might have numbers like, you might have height and weight numbers. Like you might be 71 inches tall and 185 pounds. That's a height and weight. And these pairs of numbers have a meaning. This pair would be referred to, I don't know why my computer's acting up on certain colors today. This pair should be referred to as an ordered pair. Ordered because the order does matter. The position of the number within that pair determines what it is. The first number in this case always refers to the height. And the second number always refers to the weight. And often we want to display several sets of these. In this case, it would be for several different people. There is one element or one subject, basically, that we are looking to display two traits. I spelled that wrong. You guys get the picture. Two traits, so two characteristics of that single subject that we want to display. So the key is we have to figure out some way to display those numbers and the relationship between them. Now, so far we talked a little bit about number lines. We talked about negative numbers way back at the beginning of the semester. And number lines are a very powerful tool. Now, of course, I'm not going to number all the way up to 185 here, but I'm going to use a little smaller example. If I want to display a single number on a number line, there's a couple ways I can do it. So let's say I want to display the number 7. Now, the way we discussed when we were talking about working with integers, negative numbers, was we used vectors. A vector was an arrow that started at 0 and went to the value we were trying to display. In this case, it would go to 7 to display a 7. That is a great a working display of it. It allows us to do our calculations with it. But if we're not trying to calculate with it, we just want to display the values, a more efficient and compact way of displaying it is to just put a dot at the location of that value. So we put a dot at 7. So that's not really a working display, it's just a representation of the value. But what if we have two values that we want to display together? Come on now. There it is. So let's say I want to display 7 and 4 as being linked together and in order. Well, the 7 can be marked with a dot. I could try to mark the 4 with a dot, but marking the order and the link is kind of awkward. I'd have to have not only something linking them, but an arrow or an indicator of which one came first. That used to be pretty complex. Well, a long time ago, a man by the name of Descartes came up with a solution to this. Descartes' solution was to take, starting out with a single number line, as we've always had, positives going to the right as always, negatives going to the left, and embed it with a second number line going through the 0, the origin of the first number line, but going vertically, perpendicular direction, like that. The 0 of this second number line overlapped with the 0 of the first number line. Positive numbers went up, negative numbers going down. And to display, let's go back to that 7 and 4. To display those numbers, we refer to this first variable as an independent variable. So this horizontal axis is used to display that first variable. That is the independent axis. Most often that is used as to display the variable or represented by the variable x. So also often called the x-axis. The second variable, the second number, is the dependent variable. Now, some people describe this as like cause and effect. The independent variable is the cause, the dependent variable is the effect. That's not true. One could not cause the other at all, but there is a relationship between them. The independent variable is the value that can change however we want it to. We pick a value and then we use that value to determine or find the relationship to the second value. Now, the second value would be the dependent value. So, of course, this vertical axis would be the dependent axis, or often referred to as the y-axis, because it's often represented by the variable y. Now, we use other letters to represent these variables all the time. Typically, we use alphabetical order. The one that comes first alphabetically represents that independent variable. The one that comes second alphabetically represents the dependent variable. But we do have to be careful. Sometimes the letters have meaning to the actual items being represented by the variable. So that doesn't always hold true. So now to represent that value, 7, 4, what they did this is going to be frustrating today. See if that'll do it. Nope. So anyway, we just have to tolerate the shadows here for a minute. To represent that value, there we go, 7, 4. 7 is represented on the x-axis. That would be right here on the independent axis. 4 is represented on the dependent axis. That would be right here, positive 4. Well, to represent the pair 7, 4 and the relationship between them, we project those out and up and get a single dot in that graph. That is the point 7, 4. I'm guessing that many of you have worked with XY coordinate planes or two-dimensional coordinate planes. Is there anybody, just to show of hands, anybody that has not worked with an XY graph before? Okay, so we're not going to spend a lot of time plotting points on that graph. Or at least plotting single points and naming points on, but that is something you will be required to know is, okay, if I put a point on there like this here, what is the coordinate of that point? Now the independent variable always goes first, so we follow it up to a -3, then the dependent variable goes second, we follow that over to a -8, so that would be -3, -8 as the coordinate for that point. So let's look more at what can these graphs represent and what does it mean? Well, some things we talked about height and weight. Why did we put height first as the independent variable? Now I mentioned the independent variable is the one that we can change freely. A little bit of a condition on that. You can't just pick any height you want to and find somebody who's that height. But there is a little bit of a, I don't want to use the word cause and effect, but there's a little bit of an effect there. The weight is the dependent variable because if you add weight or gain weight or lose weight, you can't expect that to affect your height. However, if you grow taller, you can expect that to affect your weight. Typically, growing taller will also increase your weight. So there is some sort of expected cause there, or some sort of expected relationship there. The height, we don't expect to change based on any relationship with weight, but we do expect the weight to change based on its relationship to the height. So that's why the weight is dependent. Your weight can be affected by your height. Now, as you graph these, there is nobody who has a negative height and nobody who has a negative weight. So most often we only use a portion of the graph, 1/4 of the graph. That's referred to as quadrant. So this is quadrant 1, or the first quadrant. As we move around the graph over here, it would have been quadrant 2. And then it keeps going. Quadrant 4 would be here. Quadrant 3, sorry, would be down here. Quadrant 4 would be over here. That has some tie-ins if you get into trigonometry as well. The trig graph or unit circle goes in that direction as well. But anyway, quadrant 1 is where both variables are positive, and in nature, that's typically what we need to work with. So anyway, let's look at labeling our axes. I'll start over now. So this is going to be our height axis. Typically, we'd want to try to start at 0 if we could, but in this case, because there's nobody who's 0 inches tall, in fact, birth height is typically, averages, between 16 and 22 inches, it doesn't make much sense to go all the way down to 0 in many cases. It all depends on what we're looking at here. Let's say we are looking at comparing height and weight of high school students. In that case, there may be no need to go below 54 inches. So we might start at 50 inches instead of 0 inches. And we number up by some sort of scale. Now in this case, we're going up to 74, so 6'2" is the tallest person we're going to have in this sample. Going up this way, for weight, well, again, normally we'd want to start at 0, but there's nobody weighs 0 pounds. So let's say the lightest person in our sample here is 90 pounds. I numbered very poorly here. I'll go back and renumber so this works out a little better. Let's do this. Still not going to get very high. So let's say our heaviest person here is 190 pounds. Notice on that weight axis, we still have evenly spaced lines, but we didn't do the same as we did on the height. Height, this is 51, 52, 53, 54, 55. Even though we only labeled every fifth marking, each marking still stands for 1 unit. Going on the weight axis, the vertical axis here, we only labeled every other one, but each marking actually stands for 10 units. This is 90, 100, 110, and so on. We have to make sure we fit the range of the data in there. Now, in reality, we would want to select people. We would measure their height and weight. We might have somebody who is 61 inches tall and 121 pounds. That would be somewhere in here. Notice 61 inches, just over 120 pounds. Getting the exact location when we have a scale on our axis like that that's numbered in tens like that is a little more difficult. One of the weaknesses of a graph is showing exact values. So as we plot several points on this graph, let's say we have somebody who is 58 inches tall and 99 pounds, 66 inches tall, maybe 130 pounds, somewhere in here. And we get those points up through there. Well, you might notice those points are not on a straight line of any sort, but we could approximate them with some sort of line or curve. That line is referred to as a regression or a best fit line. And there are several strategies for doing that. We're not going to get into that part of it at this point in this course. That would be something, if you wanted to go on to a statistics course, would be a big part of that class. This is what would be referred to as that data graph that we're going to talk about later on in this unit, because it does display real data and it doesn't necessarily fit a perfect line or a perfect curve on the graph. For the first part, what we want to look at is sets that do fit on that perfect line. What would be a line? Well, we would expect that a line would have two things. If we're talking about height and weight, and I'm going to go back and I am going to start out at 0 on each axis here, I would expect for height and weight that there isn't nobody in that lower ranges, so points would start up here, but we'd also expect that as the height increased, the weight would also increase. That's what we refer to as a positive relationship. Again, I'm not going to go into talking about correlations or anything like that, which is something that we would leave for a statistics class. But we will talk later on about direct variation or positive variation, which deals with this. But this line has a couple of characteristics. It has a starting point, and we'll define what those starting point means and how you find it as we go through the unit. And it goes up at a slant, and the slant of that is very important, and it comes right out of characteristics of the data as well. So let's look at now, how do we put points on the graph? Where do these points come from? Well, we might have an equation that looks like this. Let's say we have 11 equals 3x plus 2. If I go to solve that equation, I would subtract 2. I got 9 equals 3x. And then I would divide by 3, giving me that 3 equals x, or x equals 3. Well, very similar to that equation, I might have the equation 17 equals 3x plus 2. Well, we notice here as we break down our equation, we find our equal sign and we identify where the variable is, that the same exact things are keeping this variable from being alone as were over in this equation. So the steps to solving this equation are exactly the same as they were over here. We would have to subtract 2. We got 15 equals 3x, and then divide by 3. Only this time, 5 equals x, or x equals 5. If we kept going, we might have 26 equals 3x plus 2. Again, we notice it's the exact same steps to solve it. We subtract 2. 24 equals 3x now. And we divide by 3. 8 equals x, or x equals 8. The reason these both took the exact same steps to solve, starting out subtracting 2 first, then dividing by 3, is because this right side of the equation was the exact same for all 3 of them. There is an infinite number of equations that we could write that have that exact same formula, 3x plus 2 on the one side. We can change this number over here to any possible number and still come up with that equation, or still equate that equation. Well, that is what is referred to as a family of equations. A family of equations is just like that. It's solved using the exact same steps, but that number on the other side can change. Well, we can't write all of the equations in that family, but we can express them like this. Y equals 3x plus 2, where y is representing that we can put any number we want in there and still solve this equation. Well, we can now express this. We can represent the solution to all these equations. There we go. In a couple of different ways. We can try to list them all out, listing values for x, and then what the corresponding value for y would have to be. But there's no way we can list all of them because there's an infinite number of solutions for this. So what we do is we can graph them. And on the graph, we can draw in a curve, and the points on that curve represent the solutions to the equation. So let's do that. The way we do that graph, one of the ways we can do it is we can fill out a table where we pick values for one variable and we figure out what the value has to be for the other. Well, it's easier because of the way these equations are usually set up to pick values for y and then calculate or figure out what, or sorry, pick values for x and then calculate or figure out what the value for y has to be. So let's see what that ends up being. For x, let's do some numbers that go all over the graph. This is the negative side, this is the positive side. So let's pick some negative numbers. Let's do like -3 and -1. I'd like to use 0 because 0 is usually a pretty easy one to calculate. Let's maybe do 1 and +3. So we got numbers that are spread over. We've got -1 here, -3 here, 0, of course, in the middle, +1, +3. That should give us a decent spread of numbers. Now we'll figure out what y values have to be, and we'll plot points. That may or may not give us enough to figure out what this graph looks like, but it should give us enough at least to figure out what more we would need to know. Let me show you what I mean by that. So if x is -3, y is 3 times x, that'll be 3 times -3 plus 2. Well, 3 times -3 is a -9, plus 2 is -7. So that gives us the ordered pair, x is -3 when y is -7. So x is -3, y is -7, should be somewhere in there. So if x is -1, y would be 3 times -1 plus 2. 3 times negative, oops, that should be a -1. 3 times -1 is a -3, plus 2 is a -1. That gives us the ordered pair when x is -1, y is also -1. So x is -1, y is -1 is right there. If x is 0, y is going to be 3 times 0 plus 2. Well, 3 times 0 is 0, plus 2 is 2. So we get the ordered pair when x is 0, y is 2. Now this one can be a little confusing for some people. X is 0, which means we stay right here on that y or dependent axis, and we move up. Put some marks on here. Move up to 2, so that is 0, 2. When x is 1, y is 3 times 1 plus 2. Well, 3 times 1 is 3, plus 2 is 5. So when x is 1, y is 5 is another ordered pair. So 1, 5. This next one, when x is 3, y is 3 times 3 plus 2. 3 times 3 is 9, plus 2 is 11. So when x is 3, y is 11. Now you'll notice on this graph that goes off the range of our graph, so that point doesn't help us much. But those first 4 points are enough to figure out what the shape of this is. We can see that those points all lie in a nice, straight, perfectly straight line. So we draw our line through those points. That is the graph of y equals 3x plus 2. Well, what does that graph really mean? Well, every point on that line is a solution to this equation. If I pick this point here, I would trace that down. That is x is 1/3 and y is 3. If I put in 1/3 for x, so it'd be equal to 3 times 1/3 plus 2, the value I'd get for y would be 3. So that makes that equation true. It's going to be a point on that line. So every point on that line is a solution to the equation, and vice versa. Every solution to that equation forms a point somewhere on that line. So we can represent all of the points that are all the solutions to the equation using that graph. Now, not all of our graphs are going to be straight lines. We might have y equals x squared plus 3x minus, actually, let's make this easier on us here, x squared plus 4x minus 5. So we're going to try to graph this. And then we'll make a table to find our points. Let's do the same thing. Let's do -3, -1. So we're going to do, I'm just going to mark them on the graph here a little bit. -3, -1, 0, 1, and 3. That'll give us a nice range of points. Hopefully, that'll give us enough points that we can figure out the shape of our graph. So if x is -3, I'm not going to write all the points in because I'm going to need some space to work with these. Y is going to be x squared becomes -3 squared. Be careful that you put that in parentheses, because when you put that in your calculator, it has to be in parentheses, so your calculator calculates it, right? Plus 4 times x becomes 4 times -3 minus 5. So 3 squared is a +9. Again, make sure your calculator gives you a positive for that. Plus 4 times -3 is a -12 minus 5. 9 plus -12 is -3, plus -5 is -8. So we get the point -3, -8. So -3, -8 is going to be right there. So that's 1 point that's on our graph. Let's do the -1. Well, if x is -1, y becomes -1 squared plus 4 times -1 minus 5. Again, just replacing x with -1. Well, -1 squared is 1. 4 times -1 is a -4, and then still minus 5. 1 plus -4 is -3. Minus 5 is a -8. Gives us a ordered pair of -1 for x and -8 for y. So 1, -8 is right there. Well, that shows us one thing. I mean, we got to be careful here. If I tried to draw a line through those 2 points, it would just be a flat line. That's not going to be the representation for this graph. So let's keep going. I use the 0 just because that's an easy point to put on. So if x is 0, y is 0 squared plus 4 times 0 minus 5. Well, 0 squared is 0, 4 times 0 is 0, minus 5 is a -5. So when x is 0, y is -5. So 0, -5 is right there. Obviously not a straight line here because those 3 points definitely do not line up. Let's keep going and we'll do the number 1 for x. If x is 1, y is going to be 1 squared plus 4 times 1 minus 5. 1 squared is 1. 4 times 1 is 4. Still got the minus 5. So 1 plus 4 is 5. Minus 5 is 0. So when x is 1, y is 0. So that's going to be right here for a point. And let's try our 3 then that we'd picked. If x is 3, y is going to be 3 squared plus 4 times 3 minus 5. 3 squared is 9. 4 times 3 is 12. Then minus 5. Well, 9 plus 12 is 21. Minus 5 is 16. When x is 3, y is 16. Well, that doesn't fit real well. It's not going to make it on our graph here. It would be 316 would be somewhere up here. So that's a little too far away to be very useful here. So that point isn't going to help us. So now looking at this, we have these points. It's kind of tough to tell what it looks like so far. First of all, it'd be nice to know what happens here between these 2 points. Does it go down? Does it go up? What happens? So we're going to pick that point there is x equals 2. And then we need to know what happens over here. So we might use x equals -4 or -5 and see what happens. So let's try some of those points. The graph is telling us what points that we need to keep working with, or what points we need to try next to find spots on the graph. Let's work with, we said -2 to find this area in here. So if x is -2, y is -2 squared plus 4 times -2 minus 5. So -2 squared is a positive 4. 4 times -2 is a -8 minus 5. So 4 plus -8 is -4, plus -5 is a -9. So when x is -2, y is -9. So -2, -9 is right there. That gives us an idea what happens between those 2 points. We can see this is curving and going back up at that point. Let's pick a point over here. Let's do x equals -5. That'll be right there. So when x is -5, y is -5 squared plus 4 times -5 minus 5. -5 squared is 25. 4 times -5 is -20. And we still got the -5. But we add that up. 25 plus -20 is 5. Minus 5 is 0. When x is -5, y is 0, giving us a point right here. So that kind of gives us the picture of what's going on there. You can see that looks something like that. Now, many of you, if you've had Algebra 2, you've probably seen that, and you refer to that shape as a parabola. For this class, if we're going to plot parabolas, we're going to do a table like this and plot points just like I did. And the key to doing it, as you can see, is you pick some points and you plot them on the graph. Once you have those points, you look to see where else you need more information to figure out the shape of the graph. That's why we used x equals -2 to find this point and x equals -5 to find that point. Okay, so for now, we're going to be doing a lot of just plotting points, but we are going to look for special patterns in them. On Blackboard, as I pull this up, hopefully, you'll notice if you go into this course, under course information, if you click on the course information button, you scroll down to the very bottom past all of our class recordings here so far, you'll see I posted a worksheet on there this morning. This worksheet has 8 equations. Actually, sorry, 10 equations. I added a couple to it. There are 10 equations on this worksheet, and I gave you a table of values. Now, I gave you some values to start with. -2, -1, 0, 1, and 2. Those values of x may give us enough points once we calculate y for them, may give us enough points to graph it, and they may not. I just recommend those to get you started. You may not even use all those. You may try some other ones that work better. The reason I put them in is there's some like number 4 here where certain points work more nicely than others. So I gave you those points so you can get the graph to work out. So there are 10 equations, 10 graphs. I want you for each of them, use the values I gave you, figure out why. And if you have to find more values, find those more values and fill in the missing spots so that you can figure out what the graph looks like. Number 8 here can be kind of tricky, by the way. So that's going to be part of your homework for Friday. Another part of your homework is going to be out of the book, pages 205, 1 through 3. I'm just going to have you do all 3 of those. Those are just identifying features of the graph. And then page 213 to 217, this is again just more reading graphs on 1 through 15, the odds there. So 3 things for you to work on, the worksheet and those 2 pages out of the book. Things to notice as you are doing the worksheet and doing stuff out of the book is look for patterns. And we'll talk about this more on Friday, but what type of equations? Features of the equation. That cause it to form a line, or cause it to form that parabola that we talked about, or other shapes that you might notice that are distinct shapes. Are there things you can see in that equation that might tell you or help you predict what shape it's going to make on the line or on the graph. If we know the shape, well, then that can reduce the number of points we might need. If we know it's going to be a line, well, a line we can graph if we only have 3 points. If we have 3 points and they all line up, we know that's our line. A parabola, well, we might need a few more points, but there are features of a parabola that help us to graph it quicker if we know that's the shape we're looking at. Some things like symmetry might come into play. Especially with a graph of a parabola, symmetry is a big issue. If I know my parabola is going to look like this, if I have a point on this side of the parabola, because it's symmetrical, I know there's going to be a point on the other side of it. Okay, so I will let you guys go. That's your homework assignment, that worksheet on those 2 pages. We will see you all on Friday. Have a great day. Thank you.